Hello and welcome to a thrilling lecture on the sciences behind uranium. Hopefully you're ready to stretch your brain a little. I hope everyone learns something, but I also hope it isn't so technical that you get bored and lose interest. So let's start. Where does uranium come from? How does it get to where we find it and where we mine it? Why do we mine it? Why does drum exist? We're going to cover a variety of sciences that maybe you never thought pertained to what we do, but there won't be any math, just the fun conceptual stuff. From the physics and chemistry of its creation to the aqueous geochemistry that affects where we find it. Atoms larger than hydrogen are formed in the fusion furnaces of stars. During its normal life cycle, an average star can create elements up to aluminum. As it nears the end of this phase of its life, gravity overcomes the outward pressure of fusion, and new elements on up to nickel are created as the outer layers are crushed against the inner ones. If a star is massive enough, it experiences a rebound effect in response to this collapse. The outer layers are hurled away in a supernova, a gigantic particle accelerator. Elements from copper on up to uranium are all made in this process, as well as some of the iron and nickel that we find. Some of the dust and gas from the exploding star becomes incorporated into the accretionary disk of another star with a long life ahead of it. Over time, the dust and gas rotating in the disk collides to form larger and larger stable bodies, and some unstable ones that don't live as long. Small specks become rocks, rocks become planetesimals, planetesimals become planetoids. Some remain asteroids, and more distant ones become comets. Rocky planetoids include solid elements, of which silicon, aluminum, and iron are most abundant. Also oxygen, which is bound to most of the other elements. Some little bit of heavier elements is incorporated, including our buddy uranium. As the planetoid grows, the pressure of gravity pulling everything inward converts to heat, which can partially melt the innards. This allows denser material like iron to sink into the core. So, why is all of Earth's uranium at the surface? Isn't uranium more dense than iron? As a short aside, uranium is useful to us because it decays into other elements and releases heat. All 10 of the naturally occurring elements heavier than lead are unstable and decay this way. U-238, the most common isotope, takes almost the age of the Earth for half of it to decay. In the meantime, the large nucleus has a radius that makes it difficult to fit in with the crystal lattices and packing structures of the far more common elements and minerals formed from them, mostly silicon, aluminum, and oxygen. Atoms and molecules under pressure, which increases with depth, orient themselves to pack as tightly as they can. As these atoms pack together tighter and tighter, larger diameter atoms literally get squeezed out and wind up in the surface crust material. This is an all too brief view of the most basic parts of closest packing of minerals. It is the beginning of the part of mineralogy that makes geology majors question their life choices thus far. As mentioned, radioactive decay gives off heat. In its simplest form, a reactor captures heat, converts it to mechanical energy, and then to electrical energy by spinning a turbine. There are dozens of different designs currently, but the basic process is the same. Concentrating the fuel and then accelerating its decay produces a very rapid release of heat. Concentrated uranium fuel rods that are used up are still very dense and have been used by military research to make armor-penetrating ammunition, and of course the armoring to resist the same. Orogenesis means, what is the earthly source of uranium, and how does it wind up concentrated enough to be economical enough to mine? Uranium starts off its life as an igneous mineral in rocks, like all minerals begin. Most drum uranium comes from sandstone deposits, but some occurs in hard rock. Volcanic ash and pyroclast can contain decent relative concentrations of uranium. Uranium from this ashfall could leach into underlying sands by dissolving in water. Yes, uranium is water soluble. Plutonic rock, as it cools, can concentrate uranium by first crystallizing everything else. One theory posits that since uranium is water-soluble, all groundwater has a base level of uranium, and where groundwater encounters carbon, it concentrates. This theory does not have many supporters. Eroded uranium-bearing rocks can wash out to sea and deposit as ocean sediments. Florida drum mines are such deposits. Volcanic ash source. We saw earlier how uranium becomes concentrated in crust rocks. When crustal rocks get recycled at tectonic plate boundaries, they get barfed back up as volcanic ash. After a layer of this volcanic ash lies exposed, rain and surface water infiltrate, and the chemistry all changes. Oxidized uranium dissolves and gets transported wherever the groundwater takes it, usually through highly permeable sandstones. Plutons are underground bodies of magma intruded into overlying rocks. They melt as they get closer to the surface and incorporate melt from the surrounding rocks, as well as the chemicals from any groundwater that they encounter. As minerals crystallize, uranium and other large diameter molecules get squeezed out of the mix, much the same way as in the mantle. The metals get concentrated into more distal parts of the pluton as pegmatites, or in places where heated and enriched groundwater interacts with the surrounding rock. This image gives a brief visual description of the difference between the different emplacement environments mentioned. Hydrothermals are mineral-rich hot water veins. Pegmatites are wet magma fluid interacting with surrounding rock. Hydrothermals and pegmatites often result in what are called polymetallic deposits. Different metallic ores, if present in the melt and the water, will mineralize at different rates, creating zones or halos around the intrusion itself. Oxidized uranium is present in all groundwater in small amounts. It is difficult to successfully argue that simple reduction in place of normal background amounts could account for the economically viable concentrations needed for mining. Back to our first theory. Most of our mines occur in Jurassic-aged Morrison Formation. The upper, very colorful layer is known as the Brushy Basin. The basin part formed as a downwarp in the tectonic plate caused by North America running over another plate, the Farallon, and subsuming it. This overrun also created millions of years of active volcanism. The basin filled with volcanic ash and surface water runoff. Here we can see the extent of the Brushy Basin and the source of volcanic ash and direction of water inflow. A tiny bit of chemistry. How soluble and mobilized uranium and other metals are in water depends on their oxidation state, but also on the pH and EH of the water. Volcanic ash greatly affects the water's chemical attributes. pH is hydrogen ion activity, and EH is the electrical potential of an atom to gain or lose electrons. This graph shows zones of stability for different species of ions. Uranium-6+ is oxidized and water-soluble. When uranium transports in groundwater, encounters an electron donor, carbon being the most common one, it becomes reduced to uranium-4+ and is no longer water-soluble. Most drum uranium is found in close association with carbon deposits like dinosaur bone, petrified wood, etc. Clay particles have a surface electric charge, and uranium-4+ ions, as well as other ions, will attach themselves to them. Uranium does not always show itself visibly, but its presence is often indicated by other very visible minerals associated with it. As groundwater flows through the rock's pore spaces, different iron species indicate the oxidation and reduction state, and pyrite and marcasite, as well as altered clays and feldspars, offer a very easy to spot zone where uranium is most likely found. So, if you were prospecting for uranium out west, you would have started with a rough idea of where the gamma was elevated thanks to Atomic Energy Commission flyovers, but you would need to dial in your search. That's where geology comes in. Sandstones of the Morrison were deposited by rivers. Carbon sources collect in lower energy parts of a river, located by smaller particle sizes. Reduction zones are located by indicator minerals mentioned earlier. This is at one of the Little Pittsburgh mines in Yellowcat. The dark gray rock indicates pyrite at least, and the carbon source turned out to be freshwater clam beds. In New Mexico, much of the uranium is found in limestone beds of the same age as our Jurassic sandstones here. Limestone indicates that there was deeper water than just our simple river channels and mudflats. The volcanic ash source is the same, but here, the water carrying the dissolved uranium has to flow through cracks that form in the rigid limestone where it buckles from movement. Limestone is its own carbon source. Whenever uranium-rich water contacted it, fairly rich veins of ore were deposited. Many of the richest, most concentrated drum mine deposits are these New Mexico limestone veins and limey sandstones where carbonate is still the carbon source. This is a real-life roll front showing the different coloration exhibited by the indicator minerals, 2 species of iron and other associated minerals, including uranium. Indicated here. The darker zone of reduction stands out compared to the normal light tan color of the sandstone. This is a hydrothermal intrusion into igneous or hard rock. The bleached white halo is altered feldspar to clay minerals, and the ore-bearing halo lies just outside of that. Here is another hard rock intrusion that was originally mined for fluorite about 100 years ago. It was later found to also contain uranium. Here's a fun fact: the dark purple of fluorite indicates that it's been exposed to radioactive decay. Let's look at the common methods used to mine uranium that we see in the field. In this cutaway view, we can see more features than we need to remember. Underground ore is accessed by driving into the rock vertically, horizontally, or at an angle. Surface excavation features can sometimes be difficult to discern, or they can be very easy. Sometimes they are distinct, but quite small. A rim cut can be thought of as a very wide adit. Adits can be short, they can be tall, or they can be high up on a cliff. Adits can be created after accessing the ore seam by trenching. Shafts are not as common in soft rock mining, as the quality of the rock makes them more dangerous and likely to fail. A decline is like a downward angled trench into a downward angled adit. How is waste rock differentiated in the field? We use several criteria. Sometimes waste rock is glaringly apparent. Sometimes not so much. In cases like this, vegetation is your friend. And sometimes vegetation doesn't really help much. We've already seen how color can be an indicator. Uranium, as it's mined, occurs as one of these primary minerals. Secondary minerals like these result from the primary minerals being exposed to air and moisture, usually due to the mining process. How many of these do you have in your collection? And leave questions or comments below or email me directly. If you want to learn more, I have a ton of great material I would love to share. Thanks, and hope you learned something.